And then so now we can get into instruction set, and today we're going to be doing a deep dive into the Unity ECS transform system. Again, I wanted to bring this up kind of early on in our show run because I do think that it is a very fundamental concept of ECS and data-oriented design. There's a lot of really interesting things actually in the transform system as you kind of dive deeper and you kind of start to see why they made some of the decisions that they did for some particular things. So anyways, I'm actually going to start over in the Unity documentation for this. Reason is because I think the Unity documentation actually has a lot of really good information on the transform system. And so I don't want to spend a ton of time here just because, this stuff is all, of course, available to everybody. They can read through on their own. But I do just want to kind of bring some things up just so we kind of have like a good baseline before we start getting into some things here. So if you look over in the documentation, there's kind of the transform concepts here. So this is just kind of like a quick introduction into the main different transform components. Now, the Unity ECS transform system has kind of gone through multiple evolutions, since it's came out. And at one point they had, like separate components for like transform and rotation and scale and everything like that. So I think it's at a pretty decent spot right now. Things are kind of consolidated a little bit, but there's still kind of like some differences that this has versus kind of Unity's regular transform system. So notably, the main difference is there's two kind of main components that basically kind of track, what the transform is. So their first one is kind of the one that you'll be interacting with the most part, which is the local transform component. If we take a look at this here, you'll see that what it has is fields for position, rotation, and scale. And so this is kind of, how you can, basically set, like it says, the position, rotation, and scale of an object. The reason that this is called the local transform is because this is the transform relative to its local space. So if this is just kind of like a root entity sitting in a subscene or something of that nature, then it's going to be local to that world. However, the Unity ECS transform system is a hierarchical system, so you can have kind of child entities and kind of have like a whole hierarchical parent structure, so that now this local transform would be local to the parent's position. So you have your parent's position, and then the local transform is essentially just the offset from that. So as you move the parent around, that child entity is going to stay at that same offset relative to the parent. So that would be like, if you had a car and you want, separate wheels that can kind of spin around on their own, and maybe they move up and down a little bit relative to the car as, the car goes over bumps and everything like that. So that's kind of how you would implement something like that. Again, that local transform would be basically the difference between, say, like the center of the wheel versus like the pivot of what your car is at. And then so, yeah, this uses just kind of like pretty easy to use components for the position, rotation, and scale. So they're kind of, easy enough to manipulate. However, the other one that we also have is the local to world. Now, every component that's going to be, or every entity that's going to be rendered is going to have this local to world component. And this local to world component basically is a float 4x4 matrix. So it's a total of 16 floats inside this local to world here. The purpose of the local to world is to give the transform, or the position, rotation, and scale in world space. So no matter where this entity sits in the hierarchy of parent structures and everything of that nature, this local to world is always going to basically give the exact, world relative translation, rotation, and scale. So we kind of have these two separate components here where we kind of differentiate between a local transform relative to any parents as well as the local to world. Now, this local to world is computed in a special local to world system where it takes the transform and then converts that over to a 4x4 matrix. And then from there, it will also, keep track of, any parent positions or anything of that nature and apply those translations. Now, it's really cool because this local to world component, again, this is a float 4x4 matrix. And so if you actually look into the source code, which I can go ahead and bring up here for the local to world system, I'll have to switch my screen here. So this here is the local to world system, and you can see that there are different jobs in here for the compute root local to world job. So basically what is happening here is we can kind of look into, where am I exactly? Yeah, so we see that there's let me think about what the best part to show would be. So yeah, we can see here that when we're actually setting the, this is essentially, we can consider this the local to world for the current entity that we're going to be iterating against, because this is kind of happening in a little bit of a loop here because we're looping through all the entities in a particular chunk. So actually, I should probably showcase this because this is kind of the basic thing here. So all it really is doing is it's just taking the transform and just doing a .to matrix on it. And then it goes ahead and just sets that in the local to world. So this would be like, if this is just kind of like a regular entity, it doesn't have a parent or doesn't have any kind of crazy scaling or anything going on. All it does is just converts this local transform to a matrix. And kind of diving into this, you'll see basically what it's doing here is we take in the translation, rotation, and scale. We first make a float 3x3 matrix with the rotation. And this kind of looks to be like the most kind of, intensive part here when I was kind of going through some of this source code here. So you see that it's just kind of doing a lot of, multiplication. There's some exponential stuff going on here. So it kind of takes that quaternion and converts it to a float 3x3 matrix. And then kind of using those values from that rotation matrix, we can create our float 4x4 matrix by kind of doing some multiplications with the scale. And then you'll see at the end, we're also just passing in the translation. So there is just kind of like it's mostly basic math operations, what we're doing here. Again, just kind of creating that 4x4 matrix. Now, kind of one of the reasons that this is actually stored in a matrix, and again, I didn't write the ECS source code, of course, so this is kind of me going out on a limb and guessing on some things. But there are a lot of cool things that we can do with the 4x4 matrix that make things really easy. So for example, when we go into this compute child local to world job, this is what we would be doing if, say, we have a parent game object, or we have a hierarchical thing where we need to take the local position and then the parent's world position, and then actually calculate the world position for the child. So
I just to clarify what you said there, I can point out
yeah,
that
please.
like normally if you would do it very manually, very naively, maybe you could call it putting position, rotation, and scale, and putting them on top of each other, that would be a lot of manual work to make all of them work together to make a child of a child of a child and calculate all of that. But with a 4x4 matrix, you can just add transformations on top of each other, just multiply the next local to world onto the next, and you just going click down in the hierarchy forever, and it's just 4x4 matrix multiplication in itself is kind of a complicated thing, but like conceptually, you just put on matrices on, stack them on top of each other, and you will just get the end child transform perfectly fine, and you don't have to do a bunch of intricate work with the position and rotation, etc.
So you could either do it very manually, like you were saying, where you're like actually saying, take the position and then add the position, but oh wait, there's also a rotation on the parent object, so now we need to, we can't just rotate the child, we actually have to rotate it around the parent's position and everything like that. Whereas if we have this in a matrix, then all we need to do here is literally just this one line of code where we take the parent's local to world and then do the matrix multiplication with the local transform.to matrix of the child.
And you get the
And then if you go into the actual 4x4 matrix multiplication, you see that all it is just a lot of multiplication and addition. And the nice thing about this is with the burst compiler, this can easily be vectorized. So a lot of this can be combined into just single instruction calls. So it is pretty efficient for the burst compiler to do all this stuff here.
And just to this is very unique to DOTS. Really, it's just very, very nice to be able to see the source code straight up like this, written in a very easy to understand C# language. But traditional Unity uses the same thing. It's just hidden in C++ code in it's I think local to world matrix or something it's called. So this is even I think the old DirectX 3D that I worked with first time in 2008. This was the standard way of doing it. So this is a very the preferred way, and this is just very nice to have it explicit,
rock solid.
Like this.
Yeah. So, anyways, that's kind of a little bit of the basics on kind of why there is a difference between having a local transform and a local to world component. And then that local to world component, again, this is basically what gets actually sent over to the GPU along with the mesh data and everything like that, so the computer knows actually where to render the entity on screen. So I think there were still a couple other. Did you have something to say?
Yeah, just point out a very maybe you already a very good thing about the local to world thing instead of the matrix when you're working is you have 3 floats for the position, 1 for the scale, so you only scale uniformly in that particular case, and then 4 for the quaternion. So that means you have 8 floats for every local to world instead of 16. So just half as much memory until you get to the point where you need to figure out the whole hierarchy. So I would assume that's they could just use a 4x4 matrix everywhere and then have access function and simplification functions to be able to change position and scale and everything. And I think that's what's transform in Unity, the standard Unity basically does behind the scenes. Or something, maybe not exactly like that, but you certainly save a lot of space by having you don't actually have it you don't work with it 4x4 until you get to the point where you actually go. Work. And it's just easier. There's no real reason to have the 4x4 all the time.
You have 8 floats instead of 16. So that actually kind of leads into the next thing that I wanted to talk about, whereas you may have noticed that on the local transform, this scale is just a float scaler. So it doesn't actually do a non-uniform scale. So you can't scale it separately in the X, Y, and Z axes. You can just scale it uniformly, so it basically just kind of expands and shrinks at the same scale. However, there is a way that you can implement a non-uniform scale, and then what ends up getting added in that case is this post-transform matrix. Now you'll see that this post-transform matrix, if we go to the actual value of this is also type float 4x4. So now if you start using non-uniform scale, then now you have a whole nother float 4x4 matrix on there. And actually, one thing that I can go ahead and do is if we pull up the calculator, we can do a little bit of just quick math here. So again, a chunk is 16 kilobytes. So we can do 16 times 1024 is how many bytes are in a chunk. Now, the maximum entity count in a chunk is going to be 128. So we can divide that by 128 and we get 128. So basically what this means is that, anything under 128 bytes, that means that we'll be able to fill the maximum entity count in a particular chunk. And then anything over 128 bytes, that means that our maximum potential entity count is going to start decreasing. So if we say minus 64 bytes for our local to world, and then we minus 32 bytes for our transform, that means that we pretty much only have 32 extra bytes to work with just by default. And then, so if we also add in a post-transform matrix, now you can see that we're kind of, already just with those components, before we even add anything on our own, we're already, under our kind of max potential entity count per chunk. So it does add quite a bit of memory when we start doing things like the non-uniform scale. So that's why it's probably best to avoid using any type of non-uniform scale, and just kind of, prefer to have everything set in your, asset creation stage, have all the scaling and everything set properly, so that when you bring it over to Unity, you can, ideally have just a uniform scale of a value of 1. But if you do have to just uniformly scale up or down, then that's going to save you a lot of bytes on memory there.
And the post thing, maybe, I don't know if you're going to bring that up straight off this, but there is a slight edge case which is not supported by this setup. Imagine you're having a root object, and you have two different entities on either side, and you sort of want to scale them in just one direction so they go far away from each other because of the scale of their parents. That's not possible because the post in post transform matrix means it's after everything on the child. So you figure out everything, and then you just add the scale on the actual object, so it's not part of the hierarchy anymore. Well, I mean, I'm 95% sure that's the case. Maybe some Dots is still developing, but I remember reading something about that when it changed. So the post in post transform scales means that this only really applies because you might want to scale like the actual appearance of some end thing, and it doesn't really do anything with a hierarchy in itself. It's just like when you have figured out all the world transformed for everything, then you can individually scale things that you want to scale non-uniformly with this one, but it only applies to the child in itself.
Well, yeah, and actually you can kind of see in here in these jobs where it is actually kind of using this post-transform matrix, and basically if that chunk has the post-transform matrix, then it's just going to go ahead and factor this in. And you can see, again, it's just doing another, what is it called, matrix multiplication here on the local transform as well as the post-transform matrices.
Yeah.
The one thing that I do just want to call out on the post-transform matrix is you actually can use it for other things than non-uniform scale. So you can also do shear transforms or translating the entities relative to a pivot. So if you want to start doing a little bit more kind of, complex things with the transform where you're kind of like, projecting it onto a different, transform plane or something like that, like you can also use it for this. But, those are kind of not necessarily, the common use case.
Yeah. So that's why it's like an optional thing and shouldn't be used unless you absolutely need it. I only use like 4 times in my game, and I have hundreds of different entities. So yeah, it's not commonly necessary for really anything.
Right.
Yeah.
And then, so yeah, just real quick, kind of going through some of the parenting stuff. So there is a particular parent component. The actual like underlying data is just an entity reference. So it's basically just kind of like a pointer to, whatever entity is the parent of this particular entity. And then also we have the child component, which is a dynamic buffer, which basically is just kind of essentially a collection of all the children for a particular entity. And this kind of is important, and I'm going to be demonstrating something on this when we get to kind of a little bit of my sample project. But so we can come back to that in a second.
Just like we can go to when you show. I can continue. It's better continue what you were doing. Yeah.
Fair enough. And then so then there's kind of like a parenting system that kind of maintains this whole parent-child relationship and everything like that. And so basically, the only thing that we really need to set when we get to the code is just actually, and I'll show this when we get to it, so we can kind of come back to that. But yeah, and then just kind of going through the rest of this documentation here, I think is just super helpful, because if you go through here, it talks about kind of like using the API and like how to actually, manipulate things in the transform system. It is pretty, basic, easy to use stuff. There's this cool thing here for this transforms comparison, which actually is kind of like this essentially matrix where it has kind of the Unity engine properties and then the ECS equivalent over here. So if you're used to a lot of the Unity engine terminology, it's like, how do you do that on the ECS side? So you can see that there's all these kinds of things here, just all the basic things that we'd expect. They have some properties that don't have any equivalents. And there's also some methods. So if you want to, get children or do any, position and rotation or inverse transform point, things of that nature, it shows you how to do all this stuff here. So it's a lot of good, helpful resources as you start trying to do things that are, slightly a little bit more complicated, but definitely common things that you are going to be doing with transforms. And then transform helpers, these are just kind of some more extension methods and things of that nature. And the last thing that I wanted to point out, and we don't need to hit on this too long, is the transform usage flags. So when we're creating authoring components, we can define the transform usage flags for a particular entity. And this is how we essentially define what transform components are added to a given entity. So for example, if we say none, it means that this is basically a data-only entity, and it's not going to include any of those transform components that we were just talking about. For example, something like the renderer or renderable, it says indicates that an entity requires the necessary transform components to be rendered, but doesn't require the transform components to move the entity. So this basically just means it has just that local to world, but it doesn't have that transform component. So this would be good for something like a building that's just stationary in your world, and you don't need to move it. It can be a good way to just save on a couple extra bytes of data if you don't need. And so that's just kind of like the basics of these transform usage flags. Is you can kind of specify the particular components that you need versus don't need. So one thing to point out is you may be wondering, if you have, say, multiple of these authoring components, and say, one says, oh, the transform usage flags here are none, and the transform usage flags on this one are dynamic, and this one is renderable. What happens if you add those all to a given entity? Well, basically what it does is it just kind of like takes essentially the maximum of all of those. So it's like, whatever things that it's, adding from one authoring component, they're all just going to add, to that final entity. They're not going to like, negate out, or it's not going to go to like the lowest one. It basically just kind of cumulatively adds things up on there. So that is transform usage flags. And then there also is a section on custom transforms, and I'm going to be showing a little bit of a kind of a custom transform system that I tried to do. I thought it was being clever, but it turns out it didn't actually save me as much performance as I thought it was going to. So anyways, we can kind of go over to our sample project here. So by the way, we do have all these sample projects available on GitHub. Tobias, if you want to maybe pull up the link for that, if you just go to our GitHub organization and just get the link for this repository and paste it in the chat there, that would be fantastic. But we will have it linked kind of in the description after the live stream ends and all that. So let me see, is this the scene that I want to start with? I want to go ahead and start with a different scene, which is the spawn scene. So the idea with this spawn scene is we have a spawner here, and it's just going to spawn this stationary spawnee. If I go over to here, and this is not the spawn system I want. I have two spawn systems. Here we go. So basically I have 4 different methods essentially of spawning entities, and I'm going to be kind of showcasing the pros and cons with the different entities here. So the first one I'm going to show is just by spawning it using a local entity command buffer. This would be the same thing that we would do if we were just spawning with the entity manager directly. And what I'm doing in this case is I'm doing a local entity command buffer.instantiate, and I'm just setting the local transforms position on here. The way that I have this set up is that after I basically click the button, it's going to go ahead and pause the execution of the application, so we can kind of see a couple of the different quirks here. So go ahead and press the 1 key to spawn our entity, and you'll see that it goes ahead and just spawns this guy in the world here, and then we can go ahead and move over to the next frame, and then it just kind of is spawned in place there. So what I wanted to demonstrate with this is the pro is that it spawns in the correct place on the exact same frame, and there's no kind of delay or anything like that. The one con with this is it does create a sync point in the middle of the player loop, so that basically means that it's going to kind of force all the other jobs to completion, and that could potentially be something that we don't want to happen. But in the case if you're just kind of spawning one thing every once in a while, it's probably not all that big of a deal. But if we are doing a lot of instantiations all the time, this is something that we'd probably want to avoid. The next method is where we're using the end simulation entity command buffer system. So the idea with this one is that now this is actually going to spawn at the end of the frame at a pre-existing synchronization point. So if I go ahead and press the 2 key, you'll see that this guy actually kind of spawns under the ground a little bit. And if we move over to the next frame, then it's going to go ahead and actually move into its final position. So the reason for this kind of has to do with like the ordering of when the transform system happens. So you can see that what we're doing here is we're setting the local transform to that position of 444. But what happens is that this end simulation entity command buffer system runs after this local to world system that we're just looking at, that basically takes the local transform and converts it over into the world position. So essentially what happens is the world position still thinks it's at 000 because that hasn't been updated, because we instantiated this entity after that system took place to actually set the local to world component. So you see in the first frame, it goes ahead and it actually spawns it with the correct local transform. So we could actually look at the local transform on that one frame that it spawned, and it would say that that's in the correct position, but you see that it spawns in the incorrect local to world position, and it's rendered at just whatever is the default position for that prefab. So that's not necessarily always what we want. So another option that you see that people do a lot of times is, actually I'll skip over to number 4 here. So this is using the begin simulation entity command buffer system. Now we'll go over here, I'll press the 4 key, and you see that execution is paused, but we don't see any new entities. However, we move over to the next frame. I'm still paused from the last one. So now we're paused, and then we move over to the next frame. Then you see that it moves into view. So reason for this is because, at the end of the current frame, that entity hasn't been instantiated yet, and it doesn't even exist, so it's not there yet. However, it does get instantiated early on in the frame before that transform system runs, so that the first time that we actually do see it on the screen, it's in the correct place. So that's often a pretty good, compromise, because it does use the existing, synchronization points, but we just have that kind of 1 frame delay, which is often, not that big of a deal. The last option that I have is again using the end entity command buffer system. However, this one, what I'm doing here is I'm also setting the local to world component on here. Now, this one is probably not something that I would always use, because if we say, press the 3 key, you see what actually happens is, when we pause on this first frame here, the actual entity itself is in the correct position. It's rendered on the exact same frame and everything like that. But you can see its glasses are still in the default position. That's because we're not actually setting the local to world on all the children. So it doesn't kind of cascade down the whole thing. Of course, we could manually go through all the children and set all the local to worlds on there, but that's just a whole bunch of extra code for not really all that much benefit. So then you'll see if we do go to the next frame, then the glasses snap into place and everything is gravy. So those are just kind of like some weird quirks about entity instantiation. I just kind of wanted to like bring that up a little bit, because there are different ways that we can go about doing different entity instantiation, and there are some pros and cons for each of these methods. But yeah, so Tobias, do you have any like kind of preferred method that you use for entity instantiation? Do you have any additional comments on any of this here?
Yeah, so this situation where spawning single ones like this are, I actually don't use that too much. When I use it, I guess I mainly use the first one, but not through an entity command buffer, because I usually do the instantiate with a whole entity array.
Oh,
And
okay.
that's through the entity manager, so you don't use a command buffer in between. I
Nice.
just I have a few places in the frame where I just spawn all the enemies that I need, or spawn everything I need, or all the bullets I need, for example, and I do that through explicit sync points, which I create sometimes. I have a few explicit ones. So I guess the first one, but there's a ton of different things that is 1 frame delayed in my game. That it's not exactly precision often, but there's a bunch of stuff where end simulation and the command buffer system, that's a mouthful,
Right, I know.
where that one is used. And as you said, in saying if it's something that is not connected directly to the input of the player, I don't care if it's one delayed frame. It's just that
Right. Yeah.
the only thing I'm very concerned about, if you move with the mouse or you press a button and you want a frame, not something to reflect on the screen, that thing I have worked hard to make so it uses the first one basically, so it's
Nice.
really updating straight.
Awesome.
Yeah, but I have on the third one, on the last example, that's if you scroll down to the setting the world local to world thing at the same time. I have a
Yeah.
slightly different thing there that might be a good sample point
Okay.
for the audience. So my enemies in the game, they
Oh,
don't
yeah.
they don't care about any transform. They live in world space and they live without any parents, and they don't care. And there's nothing underneath them because they're completely GPU based, shader based animated. So they don't need any sub entities to follow them. Generally speaking, there are a few cases, but generally speaking, they don't have anything under them. So just a single entity, and they don't have a scale or anything like that, where they have a completely different type of scale thing. So I don't even have a local transform on them. Like 3 of my enemies only have their own flow 3 position that I have done in my own component, and a few of them have their own rotation as well, or all of them have rotation, I think. So, and I just work with that rotation and position in my code completely, like devoid of anything else that, and compared to the player or whatever, like are you close or are you far away, and you don't need really the local transform for that because they're not part of a transform hierarchy. And then I set the local to world in my code strict away, but since I don't have any local transform on it, there's nothing else setting the local to world. So I'm alone in my code putting out the
Right.
actual
You're taking over
global
responsibility for that. Yeah.
rendering position. Yeah, and since there's no child object under my enemies, it doesn't matter. I just write to it and it's just fine. So you can, there's a bunch of situation, and as data oriented design go, do we need the data? Maybe not. Maybe we can just throw this out. So I don't need the scale because I use a completely different situation for my
Right. Yeah.
enemies. So then you can just throw out a few floats and work directly with the data you need. And
Exactly.
yeah, so that's a fifth way, I guess, which is more or less like the third one.
Nice. Yeah, so for me, I typically like to go with the begin simulation entity command buffer system, though. Even though it doesn't spawn on that one exact frame, it kind of avoids the thing with creating an additional sync point. But you also don't get that issue where it appears at the origin for like one frame and then spawns in its correct location, because that is something that you can notice. As the player from that one frame delays, you can actually see, if you're near the origin, you can see it flash at the origin. And then, that's not necessarily a good experience because you see like, oh, did something just like pop in and then pop out? Like, what the heck was that? But, when you have that one frame delay where it's just nothing on that first frame, but then it just spawns where it needs to be on the next frame, then that's, no problem for the most part for me. Okay, so moving along, the next thing that I wanted to do, actually created a little bit of a diagram here for the player loop. So this is just kind of like super hacky version of the simulation system group. I cut it GRUs. What is that? That's what happens when you're typing something late at night. So basically, this is just kind of like the player in the player loop. There's kind of like the three main sections. So the middle section is the simulation system group where like most of your gameplay logic is happening. So what I have here is like kind of towards the beginning, you're doing your own kind of transformation logic. So you're kind of like, manipulating the local transform and things like that. And then, at some point, you probably know that you're done manipulating the transform, but you still may have some other logic that kind of takes place. And then next up, you have the transform system group where, Unity kind of takes over and does that automatic conversion of the local transform into the local to world. And then kind of towards the end, you have some of like your other game logic, just kind of other miscellaneous stuff. So what I wanted to showcase with this is how if you had like, say, maybe like a UI element that you want to follow the position of another entity, or you wanted, maybe you have some like camera target entity that, needs to match the position of the player or something of that nature. With this, I wanted to show, where you are kind of like safe to set that value for that particular entity. So you don't want to do it kind of when you're still potentially manipulating your transform, because of course your local transform could get updated later on in the frame. So then you could still potentially be using old data, or maybe even like temporary intermediate data where it's like not even ever was a valid position. And same thing with the local to world. This is going to have the data from the previous frame still at this point. So you don't want to be doing it kind of like early on. At some point, you kind of may just like know your code well enough to know like, okay, this is the last system where I'm updating my local transform logic, and I'm not updating local transform after that at all. At that point, then you're pretty safe to key off the local transform. You can say, oh, okay, that I know the position is here. That's what it's going to be rendered at eventually. So I can go ahead and use that there. However, you still don't want to use the local to world because it hasn't been set by that transform system group yet. So it's still at this point going to have data from the previous frame. So then the transform system group runs, it goes ahead and sets everything in the local to world. So after that, you're totally fine using the local to world to say, hey, this is where the position and rotation is. Let me go ahead and key off that and do whatever I need to do. You can also use the local transform as well, but I will just say, be cautious because at this point, you could potentially be manipulating the local transform in some, random miscellaneous system. But that the data in that local transform that is not going to be copied over to the local to world for this frame. So even if you manipulate that transform, it's still the entity is still going to be rendered at whatever that local to world is set as. So kind of just wanted to demonstrate that. Does that did that make sense?
For me, it makes a lot of sense. Yeah, and I'd just like to point out that this is the way that I think, if, through my experience, most game engines or most situation work. This is how you do it, and but Unity traditionally, if you use the old system transform, actually, if you take out transform dot position, the old type transform, then you do all this calculation exactly on that line, which make it really not performant. So we sort of trade the simplicity from the old type of transform system that Unity uses in the old traditional for this, where you need to be more firm with where you do stuff.
Right.
But you trade it for better performance because you don't mess around with the whole transform hierarchy every time you touch anything.
Right.
Because if you
Yeah.
just touch the anything in transform, sometimes you just get a whole cascade of recalculations of it, which is kind of weird.
Right. Yeah. So it is a performance benefit. And also we do just have kind of like more control. We can be more specific about, where things are happening. And, maybe there are some circumstances where we, want things to happen at certain places. So again, just a lot more control over that.
Yeah.
And I should point out that actually, what you just mentioned there does bring up a good point. There is a way where you can use the local transform and do I believe it's like a dot compute world matrix or something like that.
Yeah.
It actually is a pretty big, function call. You gotta pass a lot of variables into it because it actually does that whole parenting hierarchy calculation of going through all the parent entities and everything like that to figure out the exact world position of that. So that is something that you can do at any point. You can take that local transform and you can figure out what that local to world will be. But just be aware that there could be some that could be quite expensive. So it's again not something that you want to be doing all the time. But if you need to do it every now and again, that's no problem. Okay, so we have that, and then the last kind of demo that I wanted to showcase here actually has to do with some parenting stuff. So we'll go over to the samples project. The scenes, and I have this parent scene here. Okay, so with this one, we're going to be doing a little bit of kind of performance analysis. We're going to be spawning a bunch more of entities here, doing some fun ECS related stuff here. So what it's going to be doing in this case is we're just going to go ahead and spawn a bunch of these guys. So we're spawning 250 by 250. You can see right now we're moving all these guys at around 50 frames per second. And basically what these guys are doing is, if we kind of zoom in here, they're just kind of like randomly moving around. So they'll just pick like a random direction to move in. They'll face that direction and then just move forward. And then, every couple seconds, they'll just kind of like recalculate their random direction. So it's just kind of some random movement. So we can just kind of like test a couple things with the transform system here. So if we look over in the entities hierarchy, you can see what we have here is these guys, all these spawnees are just kind of at the root here of the scene. And then so one thing that, people might do, and this is kind of going back to when we're looking at that forum post, talking about some like naive things that somebody might potentially do is say, oh, I have, all these entities here. Let me just kind of clean things up and we'll put these all under a parent. So if we go over here and then we say should parent. So this is what this is going to do is if we enter play mode, you can see, oh, awesome. Look, all these guys are just under this one parent. This is so much nicer and cleaner. We can actually go ahead and we see, we got all these spawnees. But oh my gosh, look at this. We're down to 15 frames per second now. So we have, absolutely cut our performance in, just a fraction of what we had before, just by simply putting all these spawnees under the parent. So the reason for that, if we take a look at our profiler here, you see that if we look in the jobs here, you see that we have a whole bunch of idle threads for a long while, and then we scroll down, 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 and we have this local to world system compute child local to world job happening all on one single thread here. The reason for this is because when we have that one single parent, if we actually kind of go into the local to world system, and what was this called again? The compute child local to world job. So this is compute root. So yeah, compute child local to world job. So basically what this does is we basically get a dynamic buffer, and then we go through linearly all the children, and then call the child local to world from transform matrix on here. So we have to, update all these children one by one manually on one single thread here, basically just going through that buffer of all the children and updating the transforms. And again, all this stuff has to happen in that one thread, because we're just going from the parent, going through that dynamic buffer, and then iterating through each child and updating the child's transform position. So, as you can see, what we thought of just like, oh, hey, I'm just doing a little bit of scene cleanup here just by putting everything under this one parent. Well, that actually leads to some massive performance implications, because, now we have to go to this parent, and we can see that we have this child buffer of 62,500 length of all the children on here. And so, yeah, it's definitely a potential issue that you could run into. So I'm just saying, you don't want to necessarily avoid using the, parenting hierarchy. However, don't overuse it to the point where you have like many entities under one single entity, just to kind of do a little bit of scene cleanup and maintenance there.
Crazy, very crazy.
Yeah.
Just to quick callback to my quick tip here with the child dynamic buffer. That's an excellent use case for the to native array and reinterpret entity. So if you have a bunch of children and you they're not going to change, you just want to use the data straight up in a job unrelated almost, and you might do a bunch of structural changes or whatever, you can just reinterpret that to entity, so you get all the children flat as an entity array, and then to native array, and you get a copy of it, and then you can work with it however much you want. Right. I don't know, maybe they're doing something like that.
I was gonna look. It doesn't look like they're doing it here, so maybe they should hire you.
but that's because, and this is actually like sort of, I think this is probably a trade-off, but probably that they're doing it because they are on the actual parent entity working, right? So they don't need to worry about, because they are on the owning entity already and working.
Right.
But that's also like goes back to this performance issue, because they are on the owning entity. They're sort of stuck on that single one with this single thread, and when you put this 65,000 underneath it, then if you were to turn it around, maybe you can split it up and then have this copy of the child entity array and just spread it all over the different threads, and you can do it the reverse sort of update order or the reverse access order. But yeah, that's a little bit too much in that. But anyway, I use it a lot, the children to a copy of the entity array to make it easier to work with the children of something. So
nice. Nice.
Yeah.
And then, so let's see, there were kind of some other things. One thing that I don't know if we need to get into this too in depth here, but we actually kind of brought this up on last week's episode, where Danny was saying leg, but he meant linked entity group.
Ah,
I don't know if you'd caught that. So I have this add leg checkmark box here. So basically what this does is, and actually let's just go ahead and do a little bit less of these, just so I can have a little bit of better performance here. So with the linked entity group, basically this is just kind of like another buffer. So if we look at the parent here, so we have the child buffer, but then we also have a linked entity group buffer. And so this contains all the children, but also the parent itself. And so with the linked entity group, now I have these options in here where we can say disable just the parent, and that actually goes ahead and disables all the children objects. But I did notice one thing is it doesn't disable the children's children, so the glasses are still all enabled here, which I thought was kind of interesting. So then if we re-enable the parent, then all the children get re-enabled as well. Now, interesting thing to note is I believe if we go to, no, never mind. Yeah, disabled is disabled. It doesn't update the transforms or anything like that. And then also the other kind of main thing that linked entity group is used for is for destroying. So if we destroy the parent, then it destroys all the children. And this time it does destroy all the children's children as well. So just, yeah, a thing to point out on the linked entity group. Oh, and I guess I should have showed, I did say that I was going to show this earlier. We actually look into how we're spawning these. You see that the way that we actually set a parent is all that we need to do is, yeah, go here. So if I have this like should parent set, then what we do is just on the child entity, all we need to do is set the parent component equal to new parent. And this sets up a bunch of things for us. So basically what this is going to do is, if we just look at one of the spawnees, it goes ahead and sets the, that's previous parent. Where is this the regular parent? Oh, right here. So yeah, it sets the parent on here. This child comes from the prefab, so that's just kind of something automatically done. But it also gives us a previous parent, which kind of detects some changes between any parenting hierarchy. Doesn't do anything else on the child entity, but it does automatically add the child to the child dynamic buffer on the parent. So a lot of that stuff is kind of taken for us or done for us. The linked entity group is something that is not manually done for us. We do have to kind of manually populate that. So that was just what I wanted to point it out on that. And then I think the last thing that I wanted to showcase was kind of also in here. And this is kind of my custom transform system that I tried taking a stab at here. So we'll go ahead and change the prefab out for this cube. And we'll do. Okay, so what this is doing here, this is doing it's running like the exact same code, but I'm just using these different cubes here. So you can see there's just kind of doing the same random, it just picks a random rotation, moves in that direction, and every couple seconds they'll change up. So you see here that we're running around like 80, give or take, frames a second here. So pretty decent with, how many entities are we running this against? 62,500. So you can see that the local to world system, so we have the random move system processing all these, and the local to world system is processing all these here. Now there actually is a way that we can say overwrite the local to world system and use kind of our own local to world system. So what I've done here is created this turbo local to world tag. And so what this does is it has an attribute over this component, and this is just a empty data component, and this has a tag of a write group, and then we pass in the type of local to world. Now I did on the channel a while back do a video on write groups. Pretty much all of the theory for write groups exists the same as that video, but just some of the code might be a little bit different for the particular implementation details. The idea with write groups is that they give us the ability to kind of override existing logic. So again, if we go back to the local to world system and we scroll down to where we're actually like creating the queries that we'll be scheduling against, you'll see that one of the options that we add is the entity query options.filter write group. So this essentially means that if an entity has a component that targets a write group that is kind of part of that entity query, then this entity is going to kind of ignore that system. So it's almost another way of just kind of like filtering down our queries a little bit further, so we can again have a little bit more control over our logic. Now, admittedly, write groups aren't necessarily something that you're going to need to use a lot. So if you don't completely understand it at this time, that's totally fine. But basically, what it allows you to do is you can do something like this, where I have created my own Turbo local to world system. And instead of kind of doing, all this stuff in the local to world system where we're kind of like, doing some checks and balances to see if it has like a post transformation matrix and, if it has any children and, do we need to apply any rotations and things like this. I just did a much simpler implementation of this where I basically just kind of created kind of this like basic float 4x4, and you see that it uses it's kind of like similar code to what we were looking at before, where I create a float 3x3, but instead I'm just passing in quaternion.identity. So I'm going to say, hey, let's not rotate this at all. We're just going to use a scale of 111, and then we'll go ahead and create this float 4x4 matrix here. We can go ahead and actually schedule an iJob entity, and then you see that what I'm doing here is I'm just setting the local to world to that, and then I just need to set the C3 to a new float 4, and I've just passed in the transform.position and a value of 1 here. And so all this is doing is just updating just the position. So the rotation and scale should all just kind of be default here. So if we come over to the Turbo Transform Cube and I add the Turbo Local to World authoring, you see that when I enter play mode, a couple things that you'll notice is, number one, you'll see that the cubes, they're basically all just at kind of the default rotation. They're still updating their transforms and everything like that. But if we look down in here, you'll see that the local to world system is now running on just 2 entities, just kind of some default entities that we have here. But the Turbo local to world system has that full 62,500. So again, I thought I was being super clever and trying to sidestep the existing local to world system and make something much more efficient that doesn't have to do a lot of the extra stuff that the local to world system was doing. But looking at the performance results, they're pretty much the same. It's just hanging right around 80 frames per second. So that actually pretty much had no impact on performance. So it was a fun little exercise to kind of go through and figure out some different ways that I could, again, potentially sidestep some of the calculations that are being done there by doing something a lot more simple. But it turns out, I guess, the local to world system is just pretty dang efficient and works pretty well, actually. So yeah, that's kind of what I had for the instruction set. Was there anything else that you kind of wanted to add on there?
No. I can add that you are using the position here to update the position from the local transform object, right?
Yeah.
You just skipped the full transform set.
Exactly.
Yeah.
I'm not using the transform.to matrix. I'm just pulling out the transform and just setting that last column.
So it's in a way it's kind of similar how I do all the enemies in my game, because I don't need to use the right group because I don't even have a local transform, since I have my own position and rotation defined in my own component. So when you remove the local transform, you sort of also do the skipping of the whole transform system. So it's a very, very similar thing. But if you want to do what I do, but you still want to use the local transform object, then you use the right group to like, well, I still want to use the Unity built-in stuff, but I just want to write the position update thing myself. Then,
exactly.
So it's conceptually kind of similar. It's just that I sort of sidestep the right group because I just put everything into my own component instead.
Right.
Yeah.
All right. Well, now we're at the kind of Q&A portion of the show. So feel free if anyone has any questions that are related to anything that we talked about here, we can go ahead and bring this up. I do see that we do have one from Wayne Games that you had starred here. So it seems to support non-uniform scale with 11 floats, from what I understand, 4 for rotation, 3 position, 3 for stretch, and 1 for scale.
So I actually, you need the other one over. I forgot about that one. He's talking. I looked it up a little bit earlier. He's talking about probably different from that dreaming guy. I can't.
Dreaming Amlasios, I believe.
Yeah. That guy is a sort of famous person at the Unity Dots forums, and I think he made a bunch of different code structures, open source and stuff. And QVVS stands for quaternion vector scale, I think, and it's like the rotation, the position, and some shear or something. I think they stretch, and then 1 for scale. So it's like something about maybe you can if you just put in float 3 into we have the normal one, that local transform, where we have the quaternion, the position, and the scale. But if you just put in a second float 3, you can sort of get in the post transform matrix or post non-uniform scale, I think, into it, because you have another float 3 that you can sort of apply in the end, instead of having the post transform matrix which Unity provides, which is the full 4x4. I didn't look up if it's exactly what's going on, but I would assume that's sort of what's going on. And he just asked if that was something we have looked into, and I haven't. Have you heard about this?
No, I haven't.
Yeah, so I would just assume that it's basically just building in the post transform matrix thing into the local transform, so you have everything in the same again, but you're reducing the complex 4x4 scalar into just a three vector thing, where you can do the X, Y, and Z scaling like normal. But you still have, the single scale thing for the hierarchy. This thing is just for the end scale when you're just presenting it. So it's I think you should probably Google that. The viewers should probably Google that if they want to look into it. I have never had any issues with the current situation, so I haven't had to look into that framework that he's talking about. But it looks like it just takes 3 more floats per local transform, and it lets you do a bunch of other stuff with it, which, probably a trade-off some games need.
Yeah, cool. That sounds great. I also see Jeff says, I miss transform aspect. I think that was kind of, it seemed a lot more useful when Unity had like the separate transform components. Like there was a separate position and rotation and scale components, and the transform aspect is a way that we could kind of access and manipulate these all, just from one single place. But now that they kind of switched over to having the local transform, it doesn't seem to make as much sense as the transform aspect did. But did you ever use the transform aspect when they kind of like came out with that initially?
Yeah, I was right in the middle of when they was necessary before they moved into local transform. I was in there for like half a year, I think, but I don't use actually the aspects, generally speaking, because you can aspects anything basically, but I don't use it because most of the time when I would need an aspect to combine more states and more components, it usually is a good way for me to realize that maybe I'm splitting up things a little bit too much, and I can squeeze some components together into a single component. That probably is not the case for bigger games, but for my game, I rarely need to put several components into a single aspect for convenience sake.
Makes sense. Makes
Yeah.
sense.